Hello everybody! Labdien, godātie viesi, draugi un dombiedri, godātais rektori. Patiesi prieks jūs redzēt šī gada kognitīvo zinātņu, loģikas un komunikācijas simpozijā. Dear honored guests, dear friends and colleagues, dear rector, it's my great pleasure to see you all in our 9th Symposium of Cognition, Logic and Communication. I'll be very brief, and I'd like to wish you all the best on behalf of the Center for Cognitive Science Semantics in this conference. Lots of discussion, lots of inspiration in the next 3 days. I'm also especially happy that this is the largest, until now, the largest symposium we have organized. We have almost 100 participants and very high quality papers. So, and well, to be brief, I would just give the floor to the rector of the University of Latvia, Professor Mārcis Auziņš.
Good morning. Dear guests, dear colleagues, ladies and gentlemen, it's my great pleasure and honor to open this symposium. It's already 9th symposium on the theories of symposiums on cognition, logics and communication. And subtitle of symposium this year is Perception and Concepts. We are seeing that these symposiums year by year in growing in quality and growing in volume. This year we are asked to move the opening from this symposium from small aula of the University of Latvia to the aula magna, or large aula. I'm very pleased about that. And yesterday I learned that some of you, or maybe even many of you, are not only for the first time in Latvia, but for the first time at the University of Latvia. And maybe I can give you a very brief introduction to my university. University of Latvia was founded in 1919. It means that for European scale it's kind of young university or new university. But actually it cannot be older than that, because University of Latvia is a national university, a national research center, was founded a couple of months after the country was founded. And our founding fathers decided to count foundation from the university from that period, although the higher education institution in this building was sometime even earlier than university was founded. There was kind of German technical university, technical high school, mainly dealing with engineering, but it was founded in 1862. And on the basis of that German higher education institution, University of Latvia was founded in 1919. Currently we have around 18,000 students. Again, for European scale, it's kind of medium-sized university. But sometimes when I'm willing to impress my guests, I'm saying, look, it's almost 1% of current population of Latvia. It means that 1% of inhabitants of Latvia currently are students of this university. Probably it tells something about country as well. It tells that country is small. We have around 2 million citizens currently. But as I said, for Latvia it's really a very large university. It's largest university according to the number of students. We are the only one comprehensive or classical type university. We are covering almost all subject areas like humanities, social sciences, hard sciences. We have very little actually engineering, because at some point engineering departments during Soviet time were separated from the University of Latvia, and separate school, Riga Technical University, was established. Otherwise we are, as I said, covering all subject areas. We are a research university. It's sometimes very hard to measure research output in some quantitative numbers, but one of the ways to do that is count of publications in Web of Science citation index. This is what very often people who are doing university rankings are doing. And if we are doing or measuring research output from University of Latvia in this way, then we again are largest research university in Latvia. We are producing more than 50% of all research output which country is producing. Of course, it's together with our research institutes, and we have around 20 research institutes at the University of Latvia in different subject areas. Another way to measure research output is count number of PhD students defending PhD thesis. And again, University of Latvia each year is producing around 50% of PhDs produced in country. So again, we are producing around 50% of all PhDs which are coming from this country. So it means that we are really the largest university, research university, and you are very welcome to our university and to aulā magna of this university. I know that you will have many very high level presentations at this conference. I'm sure that it will fuel some discussion, and as we know, very often during the conferences, the formal presentations, it's a very important part of the conference, but informal discussions are equally important and sometimes even more important. So I hope that you will have enough time for these informal interactions, and maybe due to these interactions, some new research ideas and even maybe new research contracts and new research projects will start. I will be very happy if it will happen in this way. And also I hope that you will have time to enjoy our beautiful city Riga, with old city, and we are very close to the old city even during the coffee breaks. Maybe you can have possibilities to look what it's outside the university building. And of course, I'm altogether wishing you very fruitful and very successful conference. Thank you.
Thank you, Professor Auziņš. Actually, I would like to thank also to the University of Latvia, and particularly Professor Auziņš, for kind support of activities of the Center for Cognitive Sciences, and especially for supporting our symposium, because it's also hard work in terms of funding. Well, now I'd like to give the floor to one of the invited co-directors of this symposium, Professor Jesse Prince from the City University of New York.
So it's a tremendous pleasure to be here. I'm extremely grateful to the University of Latvia for hosting this conference. And working with Jurgis has been just a tremendous pleasure. So I shouldn't say working with, because really he's been doing all the work, and Edouard and I have just had the pleasure of assisting along the way in the most modest ways. But it's been a tremendous effort to bring together a group of this size, and that burden has fallen on him, and also a group of very, very gracious student assistants who I'm sure all of you have already benefited from and will continue to over the next few days. So I want to express my deep appreciation for their efforts in making this a successful event. I'm also grateful to everyone here in this room, those who have traveled far, those who come locally. I counted on the list of speakers 17 different countries. In fact, if a referendum goes through, it might be 18 different countries, depending on the outcome of Scotland. But this is a very international, we have a Scottish loyalist there. So it's a very international conference, but despite coming from very different places, it's a conference that expresses a kind of common voice. Reading through the really wonderful submissions to this conference, I was impressed at how much convergence there is and how many exciting new conversations are taking place. When Edouard and I sat down to think about themes for this conference, we really had no idea we would see such an exciting set of contributions for this particular topic, and we are extremely gratified to have seen that. And I want to wish you a warm welcome, and I hope that these next few days are rewarding for all of you. And I want to echo the remark made by the rector, which is that one reason for coming together and not just, say, reading each other's papers, which hopefully we already do, is it's an opportunity for conversation and for new ideas and for future collaboration. So I hope you profit in those ways as well. Thanks very much.
Thank you, Jesse. So, and now we are approaching the keynote part of today's opening session. And our keynote speaker is Professor Andy Clark from the University of Edinburgh. Andy Clark is one of the most prominent cognitive scientists, one of the most prominent philosophers of cognitive science, established the extended mind paradigm together with David Chalmers, who's also here in the room. I'm very happy to welcome Andy Clark in this our aula magna because actually, if we consider cognitive science as it is 2013, of course, one of the core components is extended mind paradigm, and this is a very big honor to the University of Latvia. Andy Clark has taught at the universities of Glasgow, Sussex, at the University of Washington, St. Louis, where he was also a director of Philosophy, Neuroscience, Psychology program, and also at the University of Indiana. He's written lots of very influential papers and some books serving the role of turning points in our current stage cognitive science. For instance, Being There, or Microcognition, or Natural Born Cyborgs. Okay, I will be brief, and I'm happy to welcome Andy Clark, and I wish you a wonderful discussion, and
Okay, well, thanks so much for having me here. Thanks to the university and to Jesse and Eduard and Jurgis and all of the organizers. It's a real pleasure to be here. Okay, let me get rid of some of this stuff and make it look right. I suspect that my slides are going to be a little bit small and far away, but never mind, because I'll just, hopefully anything that's important up there I'll say as well. Okay, there's a few people I should thank on this one, most notably I think Carl Friston and Jakob Howie. They've probably had the greatest input to this particular talk. Okay, so the topic, what I want to talk about, is something actually slightly different to embodied and extended cognition. In fact, to some of you, it'll probably seem enormously different. It all seems so different that you'll probably think that I've defected to the Cartesian opposition or something like that. But actually, I think that it will turn out that to be the case that this is the perfect computational theory of what the brain's doing to sit together with embodied and indeed extended cognition. And that's a kind of ongoing project of mine that I won't try and speak to today, actually. So what I will try and do today is just two things. I want to try and get this view on the table, hierarchical predictive processing. Just getting it on the table will take a little while, and I'm going to allow myself the luxury of not offering you any evidence for the view. There is evidence for it, and I review some of it in a BBS paper that has just come out. But actually, I think if I can just get the view on the table and then explore what it might mean, or suggest if it were true, that'll be enough. Okay, so the particular issues that I want to look at are ones to do with the co-construction of perception, understanding, and imagination, because I think that this view speaks very directly to those issues. Okay, so hierarchical predictive processing, most often known as hierarchical predictive coding, and again, there's a few reasons why I prefer predictive processing to predictive coding here, but we can get to those in discussion if you like. So these views, what they do, I think, is they turn our sort of common sense understanding of perception pretty well on its head. This is a sort of Bayesian inversion, if you like. Instead of trying to build up a picture of how the world is on the basis of lots of little incoming cues, kind of getting them together to form a bigger and bigger picture of what's out there, you try to work out what the incoming cues are on the basis of your existing picture of what's out there. In other words, the brain is trying, if you like, to guess the incoming sensory data on the basis of what it knows about how the world is likely to be. So there's a more traditional view. This is how Egner and colleagues who are opponents of the traditional view, but this is how they describe that view. They say visual cortex is viewed as a hierarchy of neural feature detectors, with neural population responses being driven by bottom-up stimulus features. Or the visual system in those views was a passive analyzer of bottom-up sensory information. These are views that Egner and colleagues want to reject. So it's a sort of Lego-type building block view of the route to sensory experience that is being challenged here, I think. What's being challenged is a view of the brain as essentially passive and stimulus-driven. So I actually think of these views as something like the kind of culmination of the program of active perception. This is about as active as perception could possibly be. Okay, so in these schemes, perception, and I've got a little caveat here that I do care about and I need to say it, perception in its rich world-revealing forms works from the top down. The reason I've got the caveat in there is that there are all sorts of ways that perceptual systems can allow us to coordinate with the world and do good things in the world. And they don't all involve the exploration of a kind of, or the top-down use of a rich world model, not by any means. So one of the challenges for integrating this work with working embodied cognition is actually to see how we flip between these two different ways of dealing with the world. And there's a nice story to tell, which I won't be able to tell today, but I will mention it, where basically the flipping is accomplished in meta-Bayesian terms. So you estimate which of the various strategies you currently have available is associated with the least uncertainty in a current situation, and you use that one. So there's a sort of meta-Bayesian route to actually using either a quick and dirty strategy or a richer one. That's a sort of nutshell version of how this is supposed to fit with embodied cognition for me. But let's try and get the view on the table first. The idea here is that the brain, in particular the cortex, is trying to predict the present sensory signal by building it for itself using stored knowledge about the world. And I've toyed with lots of different ways of trying to introduce this. The one that I'm going to use is actually quite informal. There are lots of simulation-based ways of introducing it as well, but I think I prefer the informal way that I'm going to use because I think it may give you a better sense of what it would be like, if you like, to be a hierarchical predictive processing engine sitting in the head. Okay. So on these stories, what perception is trying to do is to match the incoming sensory signal with a multi-layer top-down prediction of that very signal, tracking its evolution at many different scales of space and time. And the thought will be when that works, we perceive the world in this rich world-revealing kind of way. And when I say it's rich and world-revealing, what I mean is that perceiving and understanding here are completely inseparable. To perceive in this way just is to understand. It actually is, I think, to be in a position to reason. And it's to be in a position to imagine stuff offline as well. So I think of it as a kind of cognitive package deal. Instead of trying to get all these little bits sort of in different ways, we'll do perception in this way, and then we'll do reasoning in this way, and we'll do action in this way, and we'll do imagination in some other way. You get to do it all at once using the same basic strategy. They're co-constructed, as I'll try and suggest. Okay. So there are two key elements in the story here. The first is that perception and action depend on the learning and use of probabilistic generative models. This is a bit of the story that I think is pretty secure. I'll be very surprised if this turns out to be false. The other bit is less secure. It's the idea that perception and action depend on the attempt to use those models to predict the current sensory signal, leaving only the unexplained bits of the signal to propagate forward, the residual error. That's a kind of predictive coding aspect of the whole story. And that's empirically up for grabs, I think. That's the most radical way of telling this story. And because it's radical, I slightly prefer it because it brings some things into focus. So I'm going to introduce these ideas informally, as I said. First of all, the most important bit of this story, I think, is the basic idea of using a generative model to predict the sensory inputs. So here's an introduction that Dan Dennett gave to me, actually. So I was stranded with Dan Dennett in a cabin up in Maine because Hurricane Irene was preventing us going out on a sailboat at the time. So during quite a lot of kind of enforced space up there, Dan remembered something that had happened to him back in the 1980s. In the 1980s, a famous paleontologist, who Dan won't name for, presumably there's some delicate reason for this, but anyway, a famous paleontologist complained to Dan that his students were cheating at their stratigraphy homework. So stratigraphy is that it's these sort of geological layered strata drawings that you'll have seen. A stratigraphy drawing literally is the drawing of layers, and it's a geological cross-section that's meant to reveal the way complex physical structure has accrued over time. So the paleontologist's problem was that the students were cheating. They were just finding the right sort of picture in a book and tracing it and bringing it in as their completed homework. What Dan imagined, and this was actually built, so a software engineer working for Dan at the time built this, and they used it in some classes, was a little educational software package called Slice. Slice was a little simple user interface with a number of virtual knobs on it. Each of the virtual knobs controlled the unfolding of one basic geological process. So, for example, you'd have a little knob where if you twiddled it, you could deposit layers of sediment. Another knob where if you twiddled it, you could erode. Another knob for intrude lava. Another knob for control fracture, and so on. And you can probably, so this is a little bit like an Etch-a-Sketch in one way, and it's exactly unlike an Etch-a-Sketch in another. So those of you old enough to remember Etch-a-Sketch, I think it's out again, actually. You know, it's a little thing where you can kind of twiddle knobs to make stuff appear on the screen. So the new homework, I think you can see what's coming now. The new homework is you give the student the stratigraphy drawing, so they don't have to go out and find it. They can't copy it from somewhere. You're giving it to them. But their job now is to create the stratigraphy drawing using this piece of educational software. The important thing is, of course, that you can't do this by tracing or simply copying. The little Etch-a-Sketch here won't do that. You can't make a single pixel appear or move in any particular way on the screen here. All you can do is control the representation of these basic geological processes, representations of intrude lava, fracture, etc. So what the device is forcing you to do is to match the picture that you've been given by twiddling the right geological hidden cause knobs in the right order. That means you have to find the right knobs, you deploy them with the right intensities and in the right sequence to yield the picture that you were given. So Dan's thinking was, look, if a student can do that, then she really did understand quite a lot about how hidden geological causes, sedimentation, erosion, and so on, would conspire together to create a particular kind of physical scene, the one represented in the drawing. So importantly, remember, you can't use it like a coloring book. The interactions here are complex, they're non-linear, and you just have to get the hidden causes together in the right order to make the picture appear on the screen. A student that can do that would have to command a generative model, a model that enables her to construct various geological outcomes from their component parts as they interact in space and time. So the next step in this, to push this up a bit, is now I think the student has to command a probabilistic generative model. Because given a particular picture, there'll be a number of different ways of combining these various knob twiddlings to yield that picture. But some of those will represent geologically much more likely events and combinations of events than others. So that means you need to find the set of knob twiddlings that correspond to the set of geological hidden causes that are most likely, given all you know, to have brought about the observed outcome. So we're getting there now. This is very close to what the brain is supposed to be doing in sensory perception on these models. Next thing to do is to eliminate the student. Always a good move. So slice prime now. Now we're going beyond, of course, anything that Dan did. Dan didn't eliminate the students. They all survived this process. Slice prime is just like slice, except that slice prime incorporates its own multi-level probabilistic internal model of how geological hidden causes combine to bring about the outcomes. So you've now put into slice star the knowledge that would otherwise be in the student. When slice star receives a set of pixels specifying a geological image, it has to try to match that sensory input by unearthing the most likely set of geological causes operating at many different scales of space and time, whose interactions are most likely to have yielded that pixel array. So this is now Bayesian. This is as fully Bayesian as you could want it to be. Slice star settles on the set of causes that, given what the system knows, make the current sensory evidence most likely. It tries to account for the sensory data by self-generating it, using stored probabilistic knowledge about geological hidden causes. This is a very slim line, sort of, one domain, only perception, no action here. It's a very, it's a very slimline version of the trick that the brain uses, if the models that I'm going to be considering are right, to perceive the world. So that brings us to that model, perception as prediction. The idea here would be, well, in ordinary perception of, rich world-revealing perception, then the incoming sensory signal needs to be matched by a complex multi-level flow of top-down prediction. That match in these models is established by concurrent, it's quite important that they're concurrent actually, concurrent bouts of signal passing, in which some populations of cells send predictions sideways and downwards, and others send residual errors upwards. So basically you're constructing your predictions with lateral interactions and downward flowing causal influence within the brain, and what's traveling upwards, forwards through the system on these models, these are the strong predictive coding models, is just residual error, just the difference between that prediction and the incoming signal at that level. So we can think about this in fairly intuitive ways. If you were a multi-layer system and part of what you knew about was words, and part of what you knew about was letters, and part of what you knew about was pencil strokes on a page, then your knowledge about words at one of the higher levels here would help you predict which visually presented letter, say that's at the level below, is currently most likely. Knowing about letters at that level would help you predict what combinations of pencil strokes are most likely at the layer below, and so on. It's also important, I think, that people sometimes say, yeah, well, where does the knowledge come from in the first place? How did the right stuff get into this system to do this fancy thing? But luckily, the prediction task here is bootstrap heaven. This is a wonderful arena to pull yourself up by your own bootstraps. To predict the next word in a sentence, a really good thing to do is to know stuff about grammar. But to learn stuff about grammar, a really good thing to do is to look for the best ways to predict the next word in a sentence. So what this means is that you can use the prediction task to bootstrap your way to the grammar that you then use in the prediction task in future. And this is empirical based now. You infer the priors from the data as you go along. So now, and of course this is the hand-waving moment. Oh wait, maybe you thought it was all hand-waving before, but now this is the real hand-waving moment. Now imagine this on a huge scale. By trying to predict your own evolving inner states, using a multi-level system, you're driven to unearth the nested hidden causes, the latent variables, if you prefer, that are structuring the input signal. That's the story we've been telling. To predict text, learn about words and letters and strokes, and eventually meanings too. To predict all these other plays of sensory data that we get to grips with at all those scales of space and time, learn about other kinds of interacting hidden cause, like tables, chairs, cats, faces, people, hurricanes, football games, goals, intentions. This is a huge etch-a-sketch of the mind now on these sorts of models where you've got hidden cause knobs that control predictions that are made on the basis of causes like that, causes like cats, faces, people, hurricanes, etc. And finally, although I've almost said this already, I was in two minds about whether to include this slide, but just focus for a moment on the data compression strategy here, the actual sort of hardline predictive coding bit of the story. So predictive coding itself is a long-standing data compression strategy. It's used in motion compressed video and all kinds of places. And the idea basically is, if all that's changed between this frame of the video and this frame of the video is one little thing has moved from here to here, then in order to transmit that information, given that you had this before, all you need to do is transmit the difference. So residual error then becomes the thing that you should care about. So this kind of thought here is this is a very active brain picture. The idea is that the brain is kind of sitting there doing all of this ongoing prediction all the time. And that means that, in a way, it need only bother about whatever escapes the predictive net, wherever the residual error is. What you need to use here to drive more processing to select a different predictive model or to nuance or amend the one that you're using or to learn a new one is to attend to the residual difference, the prediction error, between the current signal at each level and the predicted causes of that signal that you're deploying from the top down. So prediction error carries the news, if you like. That's a common way of thinking about this. Prediction error is a kind of anti-hero or hero of the predictive processing family of models. So much so that, in fact, people talking about this will say, we actually don't have a forward flow of sensory information in these models. All we have is a forward flow of prediction error. We can talk about, if you like, to what extent that's a reasonable gloss on it. So in mammalian brains, if this is right, this all occurs in a hierarchical, multi-level cascade of cortical processing. The classic references here are probably Rowan Ballard's 1999 simulation paper showing how this would account for some receptive field properties in early visual cortex. And then Liam Mumford have a sort of slightly larger scale picture, and Carl Friston has the largest of all scale pictures in 2005. So, summary so far. Perception, rich world-revealing perception, occurs when the downward cortical cascade can generate the sensory data for itself using a linked series of models that have been acquired so as to capture regularity at different scales of space and time, basically. So what you see in the simulations here is that the stuff that is higher up is tracking stuff that is working at longer temporal scales and larger spatial scales. So closer to the peripheries, you're tracking stuff, predicting stuff at very fast scales of space and of time, and small scales of space. So all this, I think, recalls a dictum that I heard from Max Klaus, but I've also heard it from Rodolfo Yinas, and I've seen it attributed to Ramesh Jain. So if anyone knows where it actually came from, that would be useful for me. But it's the idea that perception is controlled hallucination. You might say, our brains try to guess what's out there, and to the extent that their guess matches, and as some say here, explains away the sensory data, we perceive the world. I'll offer a sort of flip on that later, actually, but that's what people say. And of course, this same process can sometimes mislead. This is the famous Hollowface illusion. This is Bjorn Borg, and that's what you're seeing there is actually a hollow mask of Bjorn Borg's face. So you could do this with an ordinary mask if you just took it off your face and turned it around, lit it from behind, stood at a safe distance, and observed. What you would see, even though you were looking into the hollow back of the mask, is an outward-looking face. It's pretty obvious what's going on there. It was Richard Gregory made this argument back in 1980. The strong prediction of a convex face there, that the strong bit of predictive knowledge that noses stick outward, not inwards, here gets to trump elements of the sensory input. There are elements there in the input signal specifying concavity, but they're now being treated as noise due to the strong convexity expectation, and they're simply ignored. So I'll say a word or two about the extension to action. A big attraction of this story for me is that it has a very natural extension to action, and one that reveals action and perception as inextricably intertwined, constructed in the same sort of way, using the same basic computational principles. Basic idea here is that there are two ways that you can make your predictions come out right, corresponding, if you like, to different directions of fit. In perception, you want to find the hypotheses that successfully predict the input. But in action, you predict something non-actual, and then you cancel out the error by moving your body around so that those predictions come true. So the kind of thought here is that in action, the brain predicts a trajectory of proprioceptive signals that it's not currently got, but then it reduces the prediction error away by actually moving the body so as to produce that very trajectory of proprioceptive inputs. So that's making the world conform to the prediction. So we do it in both ways, and they're supposed to interweave very delicately all the time. You want to find a model that fits the world and make the world fit the model. So an intention to this is a kind of version of the good old-fashioned idea-motor theory of James and Lotze. A kind of action here, an intention to act, becomes a sort of self-fulfilling prophecy. There's a popular book by Hawkins and Blakesley on these sorts of models called On Intelligence, and they get this quite nicely, I think. They say, as strange as it sounds, when your own behavior is involved, your predictions not only precede sensation, they determine it. Thinking of going to the next pattern in a sequence causes a cascading prediction of what you should experience next. As the cascading prediction unfolds, it generates the motor commands necessary to fulfill the prediction. So if you put all that together, you get perception and action constructed in the same broad computational kind of way and locked in a circular causal embrace. This is because your generative model in these cases will include expectations about how to use action to sample the world to determine whether the model that you're currently applying is adequate or not. So in other words, the generative model includes expectations about what will happen if you saccade around the scene in certain ways, for example. Okay, so some implications of this. The idea here is that these sorts of models perform this kind of Bayesian inversion of the standard story about perception. Instead of trying to build a model of what's out there on the basis of low-level cues, we try and predict the low-level cues on the basis of our best model of what's likely to be out there. And here's a few of the things that I believe about this process. I think this is why we get to perceive a structured external world instead of sense data. We perceive a structured external world and not just plays of stuff across our sense organs, because we have to meet the transduced pixels, if you like, with this top-down cascade of interacting represented distal causes. I think that the transparency of perceptual experience, the fact that we seem to simply see tables, chairs, and bananas, falls rather naturally out of that. They're the kinds of things that are amongst the sort of high-level knob twiddlings that would be most salient to the embodied organism. Perceiving and understanding, to the extent this is right, are co-constructed, and percepts, I think you could say, are always at least weakly conceptualized. Secondly, top-down effects will be pervasive here. What we see, taste, and feel will all be deeply impacted by what we, mostly subpersonally, predict and expect. And lastly, perceivers like this are imaginers too. They immediately have the resources to generate from the top down approximations to every scene that they could currently possibly perceive. And I'll return later, if there's time, to that caveat about approximations. Okay, so perception and understanding as co-constructed. I think that, even from the slice example, it's fairly easy to see why I would want to say that if these models were right. To perceive the world if these models are right just is to use what you know to predict the sensory signal across multiple spatial and temporal scales. What you perceive is thus influenced at every level by what you know, but what you know is constantly conditioned in that bootstrapping kind of way by what you perceive. Perception and understanding, then, are inseparable. When a system like this perceives the world, it understands it, because in perceiving it, it knows how the scene out there is likely to change across many different spatial and temporal scales. And I think that we can probably reconstruct the differences between basic and other forms of intelligence as a matter of the sort of extent of the spatial and temporal scales that you can get to grips with. As thought, sensing, and movement unfold in these stories, we don't find any well-specified or stable interface between cognition and perception. We don't find an interface at all. Believing and perceiving are co-constructed and constantly intertwined. So at this point, it would be reasonable to worry why we don't just simply see whatever we expect. We don't just see whatever we expect. It's probably a good thing that we don't. That wouldn't be a great adaptive strategy. Why not? And then there's another element that I need to inject into the model, and this is what most active research in this area is currently focused on, this element. So in these models, despite all this emphasis on top-down predictions, the actual mix between top-down and bottom-up is not a fixed mix. There are three quantities in play in these models, which are prediction, prediction error, and the weighting, otherwise known as the precision of prediction error. So that third quantity, the weight that is being given to particular bits of prediction error, can be varied according to how reliable, how noisy, certain, or uncertain different aspects of the signal are currently being taken to be. So, for example, prediction errors associated with the incoming bottom-up input should be given less weight on a foggy day, while those associated with bottom-up information should be given more weight when you're visually attending to the fine detail of a coin or something like that. So this is normally good news. We can still see very surprising things. The elephant smuggled onto stage and then, revealed by the stage magician. We can see this because under those conditions, the brain assigns high reliability to an initial flurry of sensory prediction error. A high-level theory of an agent unexpected kind now wins out to explain away that highly weighted tide of sensory evidence. It's important then that the percept that for the brain is least surprising, the one that best minimizes prediction errors or surprisal, could well be for the agent some very surprising, very unexpected state of affairs, like the elephant on stage. The elephant is improbable, if you like, but not in the relevant informational sense, given everything that's hit in the system at that moment and the context it knows it's in, unacceptably surprising. In fact, it's the least surprising percept of all the ones available given the inputs, the priors, and the current weighting on sensory prediction error. The upshot of this is that third quantity, the precision of sensory prediction error, reflecting estimates, changing estimates of our own uncertainty, and estimates that vary with different modalities, is one of the big players on the cognitive stage in these stories. These precision estimations are somewhat vulnerable. Mistakes in precision weighting, sensory prediction error, will have really, really big consequences here. So there's a nice model of the co-emergence of delusion and hallucination in schizophrenia that basically turns on the generation of false prediction errors, but then the overweighting of those false prediction errors. If you assign too much precision to your sensory prediction error, you won't be able to detect a faint pattern in a noisy environment. You might, and there are actually some accounts of autism that start from that sort of premise in these models. Or if you assign too little precision, you'll start to hallucinate patterns that aren't there just because you expect to see them. And then more subtly, if you assign high precision to the wrong aspects of current sensory prediction error, you'll miss some things that are there, and you'll hallucinate some things that aren't. And that's probably the more familiar combination, actually. So there's some famous examples of this. We can hear a famous song, if we're told to expect it, in what's really just white noise. So I think the famous song is White Christmas, and students were told, yeah, White Christmas is going to be hidden very faintly in this little sound stream. And a good number of the students quizzed afterwards said, yep, I detected the onset of White Christmas. And of course we know that we can find faces in clouds and that sort of thing. In cases like that, our active top-down model, just like in the Hollowface Illusion, I think is causing us to discard some elements of the signal. We treat them as noise, and to amplify other elements of the signal. We say, oh, that's signal, that's noise. Normally, this is good. This leads to more accurate perception in noisy and ambiguous circumstances, but not always. Here's an example from Susanna Segal. This is the angry-looking Jack example. So this is how Susanna describes it. Jill believes, without justification, that Jack is angry at her. When she sees Jack, her belief makes him look angry to her. I think it's important to get these cases going, that the actually presented signal is sort of kind of neutral, sort of on the edge. There's scope for the uncertainty to really play a role here. So given that I tried to find a sort of face that I could see as actually looking happy or angry, so I can do it with this one. If I just prime myself in the right way, I can see that face either way. In the case of angry-looking Jack, the thought is our belief primes us to deploy a model that alters the precision that I apply to various aspects of sensory prediction error. In that way, I discover visual evidence for the false and ungrounded hypothesis that Jack is angry. This will be just like hearing the song hidden in the white noise. But if that happens on these stories, visual experience then represents Jack as looking angry. This isn't a sort of add-on afterwards. This is how visual experience is always constructed on these models. And of course that adds fuel to the fire. Action and perception here are locked together in a sort of mutually misleading cycle. The primed angry Jack hypothesis gets to control actions that probe the world for confirming evidence of Jack's anger. You saccade around that face looking for very subtle evidence. You look for tension in his limb movements, oddities in his words. And so maybe I should have mentioned this, precision is a zero-sum game here. If you up the precision on some aspects of the sensory signal, you have to down it on the others. It doesn't work otherwise. So because of that, you've upped the precision on subtle signs of anger and reduced it on veridical signs of normality. So you're very likely to find the evidence that you were looking for. This isn't just a philosopher's thought experiment. Teufel, Fletcher, and Davis have some a nice review paper here showing that our active top-down models of people's current mental states and intentions make a difference to how we perceive them to be, to our perception of where they're looking, when they start to look there, the way that they're moving, etc. This is presumably important in court cases. And I think there are sort of other versions of this everywhere, you know, both in science and in everyday life. We often seem to see what we expect, and we use that to confirm the model that is generating our expectations and sculpting and filtering our observations. It's not all bad news, though. It's intuitively obvious, I think, that a familiar song played using a poor radio receiver or heard in the shower will sound to us an awful lot clearer than an unfamiliar song. You might, if you were committed to a sort of simple feed-forward story, think of that as a kind of add-on memory effect. But I think it's now reasonable to think of it as genuinely a perceptual one. The clear-sounding percept for the familiar song is now constructed in just the same way as the fuzzy-sounding percept of the unfamiliar one. It's just that the familiar one invokes a better set of top-down predictions, has a better set of priors, so it works better. Under those conditions, I want to say the familiar song really does sound clearer. It's not that familiarity makes a fuzzy percept seem clearer. It's not that memory later does some kind of filling in, affecting how we judge that percept to be. There are complexities here that I suppressed today, but one complexity is this, that if your attention was drawn to the fact that that radio has a bad sound, you'd actually be able to hear the fault in the signal, even in the familiar case. And in these stories, that's a matter of upping the precision on certain aspects of sensory prediction error. I'll skip that slide, I think. Yeah, let's skip that slide. Okay, a word or two about linguistic self-scaffolding. I think this offers a sort of framework that makes easy sense of various forms of language-based impact on cognition. So words and phrases, whether we make them for ourselves or encounter them in the world, or mentally rehearse them or hear someone else say them, doesn't really matter here. They're all cues that can favor one hypothesis over another. They can alter what we perceive, and they can make available new strategies for the control of thought and action. So there's a nice experiment from Ward and Lupjan using continuous flash suppression. This is a bit like the kind of setup you use for binocular rivalry, the anaglyph glasses kind of thing. And it allows you basically to present one image to one eye and a different image to the other one. So here you have an image continuously presented to one eye. This is, in this case, it's that sort of angry-looking face. And then a change in stream of images being presented to the other eye. What Ward and Lupjan show is that an object that is masked from awareness by continuous flash suppression can be unsuppressed, consciously detected, if the right word is heard before the trial begins. So if the suppressed object was going to be a zebra, then if you hear the word zebra just before the trial, the suppressed object isn't suppressed, and you detect it after all. They say, we hypothesize that when information associated with verbal labels matches incoming bottom-up activity, language provides a top-down boost to perception, propelling an otherwise invisible image into awareness. And Lupjan has loads of other results that seem to point in that sort of direction. There's also some nice work by Maloney and colleagues, one of those, actually it's nice, but I hate EEG experiments, to be honest. I find them so hard to understand. But anyway, it's a complicated EEG experiment with a nice result, and the result is that expectation speeds the onset of conscious visibility. Okay. So another thing about words. Words are clearly things that create expectations and can influence perception in the way that you expect in these models. But I think there might be something special about words, and it would be nice to know what it is. I wish I did, but I'll speculate slightly. I think one of the things that's important here is that the effects of words can be very, very fine-grained in a sort of a kind of sort of low-level demonstration of this kind of thing, Lupien and Thompson-Schill show that hearing the word dog is better than just hearing a barking sound as a means of improving performance in the discrimination task. So hearing the word does better than hearing some other cue that you might think ought to be cueing the very same top-down model. I think this might be suggestive regarding the role of language. Maybe language is a very fine instrument for artificially manipulating the precision of prediction error at different levels of neural processing. This might, I think, be a powerful way to think about a lot of the non-communicative cognitive effects of language. Transient, targeted, subtle manipulations of precision could selectively enhance or mute any aspect of our world model, depending upon context and current purposes. So the thought might be, look, there's a sort of artificial second system here that language allows us to wrap around our own neural processing economy that lets us reach in and fiddle with precision weighting and hence the top-down, bottom-up balance at any level of processing, so not just a simple sort of low level. That's pure speculation, of course. Okay, perception and imagination, the last one that I wanted to say a word about, as co-emergent as well. So an important feature of the probabilistic inner models that power these approaches is that they're generative in nature. That means that at layer n+1, you're capable of predicting the current sensory data at layer n, the layer below you, by means of downward connections. What that means, in effect, is that systems like this can be run from the top down, generating virtual sensory data for themselves. I think what this suggests is that in creatures like us, perception is co-emergent, not just with understanding, but with something like imagination. And actually, because of that, also with simulation, although that's another story, but that's how reasoning gets into the story here. That wouldn't mean, of course, that a cat can deliberately explore possibilities in its imagination. I think that for most creatures on the planet, acts of deliberate imagining, in some strong sense of deliberate, are simply impossible. But perhaps there's a key role for language here too, as a tool to enable us to kind of artificially seed our own deliberate imaginings. At any rate, if these stories are right, I think, any creature, if its perceptual organization is working in this kind of way, if it can perceive some state of affairs X, then it has the resources endogenously to generate an approximation to that state of affairs. Why the caveat about approximation? There's good evidence, I think, that in a lot of cases of mental imagery, you're only calling upon higher levels of the generative model. You're not using those higher levels to drive prediction all the way down as close to the sensory peripheries as you could. You drive it further down only under particular experimental circumstances where the task really demands it. So the thought would be that we effectively ignore the lower level, closer to retinotopic stuff, when we're driving the system top down in imagery mode, if you like. Conversely, online perception might have some rather special features. It's plausible to me that we can resolve prediction error in online perception at grains of level and detail that we just can't do in imagination. For example, when we attend to the fine detail of the bark of the tree and so on. It might be that that's impossible to do in dreaming and in mental imagery. If that were true, then maybe, although I hesitate to say this with epistemologists in the audience, but if that were true, then maybe when we're awake, we can actually know that we're awake, even though when we're dreaming, due to dampened critical reflection, we may not be able to know that we're dreaming. Okay, conclusions and puzzles. Perception, understanding, imagination, and action, if these stories are right, are co-emergent and they're co-determining. They're constructed using the same inner resources, and the same fundamental strategies apply. In fact, the difference between motor cortex and sensory cortex it pretty well evaporates on these stories. They're predicting different kinds of thing, but apart from that, they're doing the same sort of job. So the thought would be that what we're getting here is this kind of cognitive package deal. Perception, understanding, imagination, and action, all co-emerging in systems like this at more or less the same time. Another implication is that top-down effects are going to be pervasive in the brain and will be felt at nearly every level and stage of neural processing. So I'm going to end by briefly commenting on two common worries. The first is a worry about signal enhancement. And this is a worry that you'll have if if you focus on the predictive code inside of this alone. So the question here is, can predictive coding, a technique whose signature is expectation-based signal suppression? So, you know, if you look at the fMRI stuff here, the key experiments that suggest that this might be the right model are ones in which expected elements of the signal, of the early sensory signal, are suppressed by higher level expectation that that's how that bit of the signal is going to be. So expectation-based signal suppression, the sort of damping of response when it's predicted, that makes good sense just with regard to the straight predictive coding bit. But what about the enhancement of important or unexpected aspects of the sensory signal? You can probably see where this comes from in these models. In these models, of course, it comes from the precision stuff. So once you've got precision weighting as a tool to vary the impact of prediction error, then models like this can display these two superficially incompatible cognitive effects. You can have expectation-based signal suppression, lower-level stuff that's well predicted by your current top-level model is explained away because there's no news there. No signal propagates forward. All is left as it is. Everything's assumed to be right. That's the standard expectation-based signal suppression effect. But you can also get salience-based signal enhancement. Targeted increases in precision-weighted prediction error here are a kind of attentional effect. They sharpen some neuronal responses while dampening others. Where you predict reliable, important information in the world, response is sharpened. So, for example, if you detect a motion transient, the gain or volume on prediction error for that object or location in space will be increased, making it more able to entrain action and higher level response. So there's some nice work out there. Jahy and De Lange have a 2011 paper where they find exactly this combination of expectation-based dampening and then attention-modulated sharpening. And lastly, yes, something metaphysical. Doesn't this sort of strategy threaten to cut us off from the world in perception by inserting this rich generative model, or stack of generative models, technically it's only one, between us and the distal environment? I don't think it does. But you would be forgiven, perhaps, for thinking it does, given the way that some people talk in this literature. Patton, Skews, Frith, and Howie, in a response to my BBS paper, talk about perception as generating a virtual reality, an inferred fantasy about the world. And there's, of course, the standard talk about perception as controlled hallucination. I think we can see why you want to say something like this, because perceiving the world here requires meeting the incoming signal with this sort of model-based prediction spanning many scales. But of course, this is the very same process that reveals the world to us, that lets us get at the world. This is a process that enables us to sort out the signal from the noise, unearthing the various distal objects, casting their sensory shadows, if you like, on the wall of Plato's cave. So I think that instead of thinking of perception as controlled hallucination, we should think of hallucination as uncontrolled perception. In hallucination, if these models are on track, all the apparatus of perception is brought to bear, but with disturbed precision estimations, leading to inappropriate balances between top-down prediction and the incoming sensory signal. But it's only because we're normally capable of this very balancing act that we get to encounter the world at all, under ecologically prevalent conditions of noise, imperfect information, and ambiguity. So I think that this is perceptual openness, but it's perceptual openness for real agents operating in a real and noisy world. That's the end. Thank you.
Thanks a lot. So, time for questions, comments.
I have a question about elephants and surprisal.
Okay.
It's back to the first part of the talk. So take a case where you're surprised by what you see in a circus. It's a surprising elephant, or something surprising is going on about an elephant. And you were suggesting that an elephant is still the least surprising percept in that context. So that still seems to be, even if we grant that it is the least surprising percept in that context, it still seems to be in tension with the claim that we perceive the world to the extent that it matches are predictions. It seems like some cases of surprisal are cases when we're aware of discrepancies or disconfirmation. So the very fact that we're surprised indicates that we're not just perceiving what matches, but we're also perceiving mismatches. So that's one question. And I was also wondering about...
Maybe I should take them in order, otherwise I'll forget that before I get to the next bit. So I think the right thing to say about that is perception is still prediction in these cases. It's just that your first prediction, as it were, the ongoing prediction that nothing much is going on stage over there, turns out to be false. So you have a flurry of prediction error that has to recruit a new and better hypothesis. So maybe when I say it's the least surprising percept, sometimes I prefer to say it's the least surprisal in percept. That's to say, surprisal is this measure of the mismatch between your world model and the current sensory input. And obviously, once you've found the right hypothesis to bring to bear, now there's no longer a mismatch between your world model and the current sensory input, and it's not surprisal in. But you, the agent, are probably still thinking, well, that was a surprise. So
you think that surprise is merely cognitive in that case?
Is what?
You think that surprise is just a cognitive surprise, it's not visual surprisal. It's not genuine visual surprise. It seems like those cases...
hang on, so what's visual surprise then?
When you stare at something longer, just a bunch of physiological reactions. In that case, it seems like the fact that there is visual surprisal going on and you're aware that something is surprising, it seems like you're aware of the disconfirmation, you're aware of the mismatch. So
there's an interesting question here that I don't have a response to, so I probably shouldn't even mention it. But is this sort of question about whether we experience prediction error, whether we experience the mismatch, if you like, and I don't think we do. I think prediction error is just this thing that functions within us to bring the world into view. But some people working in music and prediction error, for example, think that we experience prediction error and that it makes a difference.
Thanks.
That was a great talk, Andy. So I'm kind of wondering, what do you include in the purview of your generative models? Because in a lot of Bayesian models, you create these latent variables just on the basis of the statistical regularities that you're extracting. Whereas I could imagine in sort of more grounded generative models, you'd also include highly constrained systems based upon like the physics of what you're seeing. So you're only seeing this collision of billiards because you have a particular physical process which would predict these responses to these collisions. So if you're allowing both to be part of your generative models, then is it still Bayesian?
Yeah, I mean, so okay, I use the word Bayesian with a kind of deep fear and angst. I think it's Bayesian in spirit, but of course, because everything that is being deployed here involves huge amounts of kind of approximation, and the model that we bring to bear to deal with some particular state of affairs in the world might be a huge simplification or even a falsification with regard to how things are actually operating in that part of the world. I think it's Bayesian in spirit because we're trying to predict we're trying to explain the data on the basis of the model rather than the other way around. But beyond that, I don't have any axe to grind over it. So it's hugely approximation based. There's one other thing that is probably worth mentioning is that when Friston does this sort of stuff, everything gets to be part of the generative model. So your morphology would be part of the generative model that you bring to bear on the world. Whereas another way of thinking about it is that that's a sort of background condition that the generative model that is formed, say, in cortical processing, can just take for granted when it has to work out, what to predict out there in the world. And I actually slightly prefer the non-Friston way of talking about it because once, the bacteria is a generative model of its environment for Friston. And it disturbs me slightly, I know what he means, but I don't know, the thing you were asking about physics at the beginning, I don't think I got to grips with it, I didn't quite get it. What was the...
You could have completely statistics-based ways of creating these latent variables, and then when you're trying to explain something, you're going to be combining, partaking of these different latent variables and different recombinations to explain what you're seeing. But there'd be a way that seems a lot less pure probabilistic reasoner, which would be say, well, you know, we actually have models of how bodies move that are subject to physical constraints, not just these probabilistic constraints. Or with the billiard ball example, we have these mechanical models of what happens during a collision, and that's constraining how we're seeing things, rather than just pure probabilities.
I see. So this is kind of a question about the content of some aspects of the generative model. Is it all best understood just as probabilistic expectation all the way down? I suppose what I kind of think, but I can't prove it, and we should talk about it, is that what we gloss perfectly correctly as a model rather than a probability density distribution is actually implemented as a grip on a probability density distribution. So I think that the model picture here is one that we should avail ourselves of as cognitive scientists, and Aaron Sloman has been arguing about this stuff a bit. But then you ask the question, how do you implement that model? And I think that our best clues about implementation are all probabilistic generative models that are dealing in density distributions. Anyway, we can talk about this after, I guess. That's a good case.
I wonder how the perception-cognition distinction works on this kind of model. I mean, I take it the idea is not that the contents of perception aren't actually the contents of the sensory signal; they're the contents of the model that generates and predicts the sensory signal. But on the face of it, the model that predicts generates and predicts the sensory signal is going to have all kinds of stuff that doesn't correspond to things we'd ordinarily think of as perceptual content, right? There's stuff going on behind the curtain.
Very low.
My best world model will say that people are walking out from behind the curtain, and that's part of what's going to generate my predictions of the signal. We'd normally think of that as more of a kind of cognitive representation than a perceptual representation. On your model, why don't these just collapse?
So there's sort of two issues there, I think, or at least two issues. One is a sort of question about how to sort of pin the phenomenal kind of tail on this donkey, because there's all sorts of probabilistic prediction going on here, and some of it doesn't actually seem to us as if it's part of our conscious experience, like zero crossings or something like that. So I think that will come down to stuff about the sorts of embodied interactions that for systems like us make salient information available. So the stuff that will become highlighted in phenomenal space is the stuff where an agent controllable interaction can do something good to the incoming signal. So that's a sort of quick thought about that. As for the question in general about perception and cognition, another way to think of one way to think about it is that the higher levels here could be thought of as high-level percepts. There's a kind of Gibsonian way of thinking about the high levels here, where they're sort of, if this makes any sense, abstract perceptual states. So a very, very high-level percept predicts a whole multimodal flow of activity. Pardon? Yeah, that's true. Yeah. Well, if I think of you without the kind of linguistic overlay, then I think I can get away with saying something like what you're describing here is just the fact that your model involves high-level perceptual states that have sort of flow-in sets of multiple spatial and temporal scale predictions coming from them. So even if Rob was in the coffee bar, you could still have that particular thing going on. was something else I was going to say, but I forgot what it was. Hey.
So perhaps two last questions. And,
so I can see how the model is extremely effective So I can see why the model is extremely effective for a lot of perception. And I was just a little bit worried about bodily sensations and particularly pain for a couple of reasons. And firstly, it seems that it's hard to understand pain in terms of just purely indicative contents. You want something like imperative contents, ways you should respond. And secondly, the very notion of perception as hallucination. I mean, it seems tricky to even make sense of the idea of hallucinating pain as opposed to actually perceiving pain. I mean, people might disagree on that, but certainly pain doesn't seem to be easily captured within the notion of a mere prediction about how things in the world are.
That's not obvious to me. I mean, the pain signal seems to me to be as much a part of the nociceptive prediction seems as good as any other kind, and as apt for the sort of as apt for going wrong if you have the wrong balance between top-down prediction and bottom-up sensory signaling. I think the pain case should fall quite well out of this, actually, given all of the the sort of top-down effects on how we experience pain. But it's an interesting case. I mean, another one, of course, is smell, and there is some nice work on prediction and smell as well. And I know that also I did remember what I meant to say to Dave just before there, which is there's a whole other story, Dave, to tell about what language does to this. So when I try and predict your behavior, part of my model is that you're a propositional attitude type agent that has a grip on yourself as an agent in those terms. And that's gonna make things complicated. So the pain case. Let's talk about it some more afterwards, because I think it would be very bad news if it didn't deal with that case, I think.
Okay, now the final question. Unfortunately, we are a bit out of time, so we'll start a parallel sessions 10 minutes later. So, but the final question is about Jess.
Thanks for a wonderful talk and a great way to start the conference, Andy. I want to ask something about the grandeur of the picture, because you've given us a kind of programmatic formula. Perception is prediction, and you've said that like almost as if it's a general theory of the mind, like connectionism, classicism, and now we have prediction theory, forward coding, all this kind of stuff. But the problem is perception does all kinds of things pervasively. It sharpens. It calibrates things that occur in the nervous system at different points in time. It does something that's almost the opposite of prediction. It uses the sort of present, or you think about these time cases where the past is rewritten by the future or something like that. So there are all kinds of ways in which perception is integrating information at different time scales. So we could talk about general principles of perception, and suppose, just take the simplest one, which is sort of sharpening. There's filtering to get rid of noise. Yeah. So why not just say perception is noise filtration? Why pick one of the general things perception does, maybe contingently? I mean, these are ways to improve perceptual information. Use prior knowledge to improve perception, but you could also use resolution filters to improve perception. All of these seem to be not the essence of perception, but among the important and pervasive tools in the perceptual tool belt.
So, I can see a challenge, a reasonable one about why pick that particular phrase out of all of the phrases that you could have used to describe this whole space of models. And I think the response to that is that the good thing about the prediction machine kind of story is that I think it gives you a framework into which you can easily slot all of the things that you mentioned, all of the things about, salience-based signal enhancement and, embodied action, direct perception kinds of stuff. I think we can slot all of those in very neatly by, for example, thinking that a really important job of the rich world model is to let you know when a thin world model will do, that kind of stuff. So I just use it as a sort of I like perceiving as predicting just because I think it gives us a handle on an overall economy in which there's loads of things going on, but they all have to make sense within an economy that is based on probabilistic generative models. So I could call it perception as always based on probabilistic generative models, but it didn't sound quite so punchy.
Okay, thanks a lot. and we are. And now we are starting our parallel sessions. We are a bit late. We will start in 10 minutes, and we are also distributing direction signs all over the building, so you'll find the relevant room as soon as possible.